Welcome to the SONUS 2007 demonstration. SONUS is a program to develop self-organizing networks of unattended sensors. It has an in-house component and a university component. The university component addresses detections, while the in-house component, demonstrated here, addresses the problem of organizing a distributed network of heterogeneous assets to move data from where it is produced to where it is needed. What you are seeing is real running code. The scenario is simulated, but the algorithms are real. To simplify understanding, we've assigned different kinds of data different colors. The inside ring of each node shows the colors of data desired, and the outside ring shows the colors of data produced. The arrows indicate the flow of data between nodes, and the weight of the arrow shows how much data is moving on that path. As you can see, the data generally ends up in the right place. In this first experiment, the node labeled A is the only producer of orange data, and the node labeled E is the only consumer of orange data. Neither node knows of the other's existence. Orange data originating at A does not know where it is going. The nodes have no shared knowledge representation, nor do they have any global knowledge. They sense their local environments and know only who their immediate neighbors are, and each node has far more data than bandwidth to deliver. The node labeled G quickly specializes its behavior to become a middleman for information, taking data from A and passing it on to E. There is no code for G that tells it how to be a middleman. Middleman behavior emerges as a consequence of many more primitive actions available to G. When we killed off G, which could happen for many reasons in a real network of unattended sensors, the nodes had to adjust their behavior. Each node has both exploratory and exploitive behavior. When G died, messages trying to exploit G's middleman value were not rewarded, but exploratory messages from A to C did receive a reward, encouraging that channel to be exploited subsequently, and a path from A to C to D to E quickly formed, once again delivering the orange information to the most favorable recipient. When G came back online, the shorter A to G to E path reasserted itself. Something happens at node D. We don't care what it is, but D now wants orange data in addition to its original desire for red data. Paths quickly formed so that both D and E receive orange data, and both C and G specialize as middlemen. This next experiment is about scalability. We wanted to eliminate shared knowledge representation so that we could scale across time. With no shared knowledge representation, we can augment the initial deployment of sensors with new sensors, whose missions were unimagined at the time of the initial deployment. The new sensors will interoperate with the existing sensors because neither generation has preconceived ideas about how the other works. This makes it possible to build a SONUS system that evolves its behavior to suit an evolving mission. Similarly, we eliminated any dependency on global information in order to scale across space. Our recent work has focused on two such spatial scalability issues. The first, exemplified in this experiment, has to do with what we call leakage. In the first experiment you saw, our network was right-sized to the events we were trying to observe. The experiment you are currently watching explores what happens when the events are small in comparison to the extent of the sensor constellation. In other words, if we don't know in advance where interesting events will occur, can we lay down a large network and still detect the events? This experiment embeds the first network in a gray network and asks how much of the interesting data leaks out to the gray nodes. Once again, all of the nodes have far more data available than bandwidth to deliver, but most of the nodes do not have data that is interesting for the event under observation. What we see is that very little interesting data leaks into the gray, and the same patterns form in around the events of interest, and the same nodes specialize their behavior in the same ways as in the first experiment. While it does take slightly longer for those patterns to form, the settling time appears to be asymptotic. With half as many gray nodes, the settling time is a little lower. With twice as many gray nodes, the settling time is about the same. An interesting result that we did not initially expect was that when we suffer a failure in the network, this larger network actually repairs itself faster than the smaller network did. This appears to be because the gray nodes provide some alternative paths of short length between producers and consumers of information. This is the kind of scalability result one would hope to achieve. In order to prove these results, we needed to do more than just observe the behavior in this visualization. The SONUS components have probe points, which allow us to inject a wide variety of measurement instruments into the system at configuration time. For instance, we can measure point-to-point throughput. Our probes use the Java logging facility with networked log handlers to report measures to a common location for post-processing. We call this common location the distributed logger. This doesn't violate the assumption about global information because this common location is only present for measuring and validating the system, and the metrics can be turned off at configuration time. The displays you see are actually plugins to our distributed logger. Other plugins, which we do not show here, provide charts and tables that validate the results we have described. In the near future, when we move our scalability experiments to our compute cluster so that we can expand the experiments to hundreds and thousands of nodes, the distributed logger will be an even more important component of our testbed. This third experiment tests scalability across larger events of interest. In the previous experiments, we have seen nodes quickly specialize their behavior to become middlemen in chains of length 2 and 3. This raises the question of whether longer chains can also form. In this experiment, we require chains of length 6 and 7 to form. We have chosen the target path lengths of 6 and 7 because those are typical time-to-live lengths, or TTLs, in a wired network. In other words, we are forcing our messages to travel, at a minimum, the maximum number of hops that packets in a wired network travel. But in the wired network, messages know their destinations from inception, there is sufficient bandwidth, and the topology remains stable. All of these assumptions are violated in the kinds of military operations we envision for SONUS. We have tried to make this a difficult experiment by constructing the network so that there are many paths that look promising at first, but then lead to dead ends. We have also made sure that there is an articulation point at node M where the traffic bottlenecks. Once again, there is far more data than bandwidth to deliver, and so the purple, orange, and gray messages all have to fight for survival at every hop, especially at the bottleneck. Then, to make the problem even more difficult, about halfway through, we kill the bottleneck node at M and make the traffic go in an opposite direction to find its way to a consumer through a new choke point at G. As you can see, the messages in this SONUS experiment find their way past these obstacles, and the data paths that emerge are not just efficient, but also optimal. Likewise, the network responds to hard failure of the most critical nodes, and the surviving nodes are able to unlearn behaviors that were once successful, and learn new behaviors that allow them to adapt to the new setting. Although it does take more time to develop longer paths from producer to consumer, this is consistent with the conditions of a stable network. It is more expensive to deliver traffic via a long path than it is to deliver traffic via a short path. Ideally, we want the network to develop short delivery paths where possible, and long delivery paths where necessary. And the messages delivered on those long paths should be very important, because at every hop they are crowding out other messages that are potentially more economical because they have consumers closer to home. There are several areas of ongoing SONUS work. One involves extending the scalability experiments to much higher scale, using our compute cluster, our distributed simulation environment, and our distributed logger. Another area of ongoing work deals with developing a better understanding of the machine learning that occurs on each SONUS node. A third area of ongoing work involves making more behaviors available to each node. Currently, a node can consume or forward a message. In the next version of SONUS, a node will be able to add processing to a message, possibly fusing it with other local data and then forwarding the fused result. This will allow a wider variety of specialized behavior to arise at a node. Moreover, we would like the primitive behaviors to be as fine-grained as possible so that SONUS nodes can better tune their personalities to the evolving mission.